let us start by just an introduction to the topic, dance notation and robot motion. I would like just to give you in some sense the story, the origin of this workshop. We are working from several years, I will say more than 30 years, about robot motion planning and control. Mainly we define how a robot can decide by itself on the motion he has to perform to perform a given action. Okay, and then we arrive at some stage to that question: how to define a motion-based language. Imagine that you have to make a robot programming. Then you can use a very sophisticated language which is very obscure, but the objective will be to control or to ask the robot with perhaps a natural language. But there is a huge difference between the natural language and the motion the robot has to perform. Why? Because the robot is completely stupid. It's a machine, and it has just a computer, and the computer has to give the work. Then how to transform this level of abstraction, like a language, into effective motion. And perhaps to help that, it could be interesting to promote the idea to have a motion-based language. That means a language which is closer to the machine, closer than the natural language we are using. And then I would like just to give you two examples with the robotics perspective about this question. And the workout example, you will be surprised, certainly, is that one. How to park your car. Okay, then we are very, very far from the dance, and we are very far. And then, how you are? Okay, then.
With this kind of car, yes, this is.
You are right. Thank you, Jean. How to park your car? That means that don't forget that you learn driving a car. It's not an easy task. Then imagine now that we have a robot, and we would like to have this car parking itself in an autonomous way. And you know that this is already done. It's possible to write some... okay, then what has been the key issue to solve that problem? And that problem has been... the very first results has been done at LAAS during the 90s. Okay, then the question is, the car is at that position here, and we would like to park it. How to do that? Then you have to generate a motion, okay? And this motion, as you can see here, there is a lot of maneuver because the place is not so right. Okay. Then, in some sense, we solved the problem. How did we solve the problem? And in fact, it has been possible to solve some easy instance of the problem, which is how to go from a position to another one here, to that position, to that one, by the shortest path. I would like to have the shortest path to do that. And of course, you have some constraints to move. The car is rolling. Then how, okay. And then how to go from that position to that one? How to go from that position to that one? And it appears that this is a mathematical problem, very simple, because this is not an articulated body, this is just a rolling body. Then it is very, very easy. And then it's possible to prove that the shortest path is made of straight line segment and arc of circles. Okay? And then that means that the theory, the mathematics, tells you that make a combination of arc of circle and straight line segment and you will succeed. And in fact, it has been possible to exhibit the family of words, which is arc of circles, forward, backward, arc of circle, forward, arc of circles, which is exactly that one. Or for instance, that one is arc of circle on the right, arc of circle on the left, for backward, reverse the velocity, and arc of circles. And there are finite numbers of words. And just by combining all these words, it's possible to solve the problem of parking a car. Then in some sense, this is a language here to park a car. Okay? Second example here. I would like to show you here the humanoid robots HRP2 you will see in this afternoon, and is performing two tasks. One is to pick that ball here, and one is to reach these both balls. Okay, and you can see the motion. Okay, then this is the same motion, but by reducing the velocity. And then my question is, look just at the motion. Is it possible to make the difference between these two motions here? Again, here there is one task which is to reach that ball, while here there are two tasks which is reaching both balls. Of course, this ball has been placed exactly at the placement of the left hand. But there are two experiences. Here we ask the robot to reach first that ball, and in the second experience, he has to reach both balls. And then the question is, are the motion the same? Apparently, yes. In fact, no. If we superpose here both motion in that picture, you can see some very slight difference on very slight on the left hand. Okay? There is a slight difference. And in fact, now, if you observe the function that gives you along the time the distance of the left hand to the terminal position, to the end position, it appears that the curve in the first case is like this, and in the second case, the curve is like this. Then there is a difference. And what is the meaning of the difference? The meaning of the difference is that, of course, we have programmed the robot to grasp an object. What does it mean to grasp an object? To grasp an object means that my hand should be close to the glass. Okay, that means that the difference, the distance between my hand and the glass should be reduced, and should be reduced according to some law, and this is a law here which has been implemented. But this law is not neutral. This law tells you the way the robot will reach. And if the robot follows this law, then necessarily the curve should be like this and not like this. That means that the slight difference has a deep meaning with respect to the action to be performed. That means that the way to go characterized the action which is performed here. Okay? And then if we gather all the examples, I want to write motion, okay, to make the scoring of the motion, okay? And then motion notation is a matter of motion segmentation. What is the vocabulary? What are the words? Okay, and motion generation. How to translate the word into an effective motion. Okay, then let us speak a little bit about the purpose of this meeting, because we are interested, of course, in humanoid robotics, and half of the assistants is interested by that, and half of the assistants is interested by that. Okay, that means that the human body. And what is the ambition? The ambition is to account for both what I call the body space and the space of the body. The body space is just the posture and how to describe a posture in the space, while what I call the space of the body is how to locate the body in the space. And then this is very well known from the robotics people, because here there are mainly, most of the time, some redundancy with respect to a task. There are many motions to grasp an object, while here there is an under-actuation. That means that to move the body in the space, you have to use the internal degrees of freedom which are here. Okay, and then the key point, of course, for today is that human and humanoid robots share exactly the same morphology, not exactly, share the same morphology at large. The same morphology, if we consider, for instance, the Laumond's body model, which is quite simple, because this is exactly the same model we are using to model our robot here. Okay? And then the question is, since there has been a lot of work about dance notation, it seems clear that if we want to describe that motion on a human here, we may apply dance notation. There is no reason, of course, that this notation does not apply for robot motion, okay, to make the description of the robot motion. And this is what we did. And more precisely, this is what NAOCO did, okay, by notating this rather complicated motion here, which is to grasp the ball here. Okay, then for the specialist, here you may recognize I think that the ball is here, and NAOCO? No, it's here. Yeah. Okay, and okay, and then this is the scoring. Then, of course, Jacqueline Chaleas will introduce this notation here. This is a scoring of the motion where the time is vertical. Okay, then it's not exactly like in music where the time is horizontal. Here the time is vertical, and there are several symbols representing the body space. Then we will. And then now the challenge is how to use computer engineering techniques, perhaps, to make an automatic scoring of the motion, and by using the technology, for instance, based on motion capture. At that stage, NAOCO did that by hand, how to make an automatization of that. And that I know that several of you in this room try to answer that question. And the second question is, then this is motion segmentation. And the second question is about motion generation, in the sense that now if I give you that scoring, how to provide that motion. And there are the question to be answered. And if you are, sorry. If you are considering this scoring, which is completely obscure for the robotics part of this room, the computer science part of this room, but which is, I think, very clear for the most of you, I would like to insist on a notion we start discussing with Noël Simonet during our last meeting, when I try to say that for us, what is important in robotics is more than the body space is the action space. That means that I want a robot to grasp a glass. I don't care about the exact motion. Then I don't care, in fact, about the body space as such, as a description. And for me, at first glance, I thought that the Laumond notation was only about the body space, but this is not true, as you explained to me, and there are symbols here which are very simple that just design the fixed point on the effect of the motion, which is what I will call the action. Then it's possible to make a summarize. If you want, for me, grasp the object is just a symbol, and that's it. And it appears that it's possible to also use the Laumond notations to make that. Then this is one of the topics we will have to certainly to discuss. And then to conclude, the key point for us is which place for the symbols. At which level we have to give a status to the symbol. And I would like here just to remind a sentence by William Forsythe I like a lot. The vocabulary is not and will never be old. What you are doing avec the vocabulary is another story. Eh? You know, that means that the vocabulary is the most important. After that, you can write. Okay, you can write, but the quality of the writing is the. Okay, okay then, thanks for. Thank you all for coming. I think that the challenge now for us will be to try to reach a mutual understanding. Okay, to see what are the questions you are asking, what are the solution you are exploring, how it's possible to make a synergetic research. This is definitely the challenge of this workshop. And I would like truly to insist that don't be afraid. It's a very friendly workshop, and then you will have some equations. I ask all my roboticist colleagues in robotics not to put too many equations, but I'm truly sure that there will be equation, and you have seen there were one equation in my talk. And then, but the key point is truly to understand this further. I would like, since I am thanking you, I would like to especially thank Naoko Abe, who helps me in organizing this workshop, with also Marie-Agnès Bellière, who welcome you. Okay, then, thank you for coming here, and I would like just to conclude on perhaps, I don't know if you have identified that picture. This is very, very interesting picture, and it comes from a dance instruction manual by the famous painter Oxai. Okay? And there is a very nice exhibition at that time in Paris. And this is truly a dance manual instructions. And but all these notations are somewhere say that you have to move the foot, you have to. Okay, then this is truly a very old dance notation system, which is not exactly the goal we are looking for, because the abstraction here comes from the drawing, and while our ambition is truly to have a language that can be written. Okay, then let's the workshop begin. Okay, thank you very much.